Alright, let's take a look at Diels-Alder reactions. Before we do that, let's first of all see what kinds of dienes are possible. Dienes are compounds that have two double bonds, and there are three combinations that we see that are possible. The first one is conjugated, where we have an alternating system where it's double, single, double. We've got cumulated, where we've got two double bonds connected to the same carbon, and then we've got isolated, where we have more than one single bond between the double bonds. The ones that we're most interested in will be the conjugated systems because we can get orbital interactions between these two double bonds. And that's what the Diels-Alder reaction depends upon. And what it is, it's an electrocyclic reaction, and we get a similar arrangement of electrons during the transition state to benzene, where we have 6 pi electrons in a cyclic electronic array. So let's take a look at an example of that. We've got two parts to a Diels-Alder reaction. We've got the diene, which must be conjugated, and we've got the dienophile. Dienophile means we've got something that likes dienes, and dienophiles are generally compounds that have one double bond, while dienes have two double bonds. And what we're seeing here is the electrons from the dienophile forming a new bond between the end of the diene and the carbon from the dienophile, and then we get this double bond moving towards the middle of the diene system. Then we get this double bond forming a new single bond between the end of the diene and the dienophile, and this creates a ring. Now the whole reaction is concerted. That means it all happens at the same time, and this is evidenced by the fact that we're seeing all these arrows into one structure. The other thing we notice is that we're getting a stereo-specific interaction going on, because we start with the cis dienophile, we'll end up with the cis ring. If we start off with the trans dienophile, we'll end up with the trans ring. Now, let me give you a little bit of background into the orbital interactions that we're seeing with the diene and the dienophile. So what we're looking at here, this is an energy diagram for the diene, and we're just interested in the pi electrons here. And here we've got 2 pi electrons and 2 pi electrons, that's for a total of 4. And here is what our energy diagram looks like for the pi electrons. Now the lowest possible energy will be the situation where we've got all the p orbitals lined up with the same phase. So we've got all blacks across the top here and all whites down the bottom. So remember, each of these represents a single p orbital. The next highest energy one, next lowest energy one, is where we've got 2 blacks down here and 2 blacks up here. So we're not getting quite as much overlap between the p orbitals here. That's why this state is going to be of higher energy. But let's not worry about the anti-bonding ones at this point. We'll just worry about the 2 bonding ones. And we've also got the ethylene over here, or this is just a one double bond. And the lowest energy one is where the 2 p orbitals are in phase, where we've got the 2 blacks on top and they're matching. And the worst possible arrangement is when we've got the black up here and the black down here, so they're not overlapping at all. Now the Diels-Alder interaction itself is based on the interaction between the LUMO, which is the lowest unoccupied molecular orbital of ethylene, and the HOMO, which is the highest occupied molecular orbital of the diene. So we're looking at this interaction here. And what we can say is that the closer these two are, the more favorable the interaction will be. And what we notice is that adding activating groups or electron donating groups to the diene will tend to raise the energy of the HOMO, while adding electron withdrawing groups or deactivating groups to the dienophile will lower the energy of the LUMO. So you can see here the difference in energy between the HOMO and LUMO is this, but then when we add the electron donating groups, it lifts the HOMO and lowers the LUMO, and you can see now that the energy difference between the two is a lot less. Now the closer these two are in energy, the more favorable the reaction is going to be. That's why you'll often see electron donating groups on dienes and electron withdrawing groups on dienophiles. Okay, let's take a look at a couple of examples of those. And here we go. So in this case you can see we've got a diene and we've got a dienophile here. And what we're going to do first is arrange this so that we've got something similar to what we've got on the PowerPoint slide. And we know that the Diels-Alder reaction has this kind of arrow. It doesn't really matter which way the arrows go, whether it's clockwise or counterclockwise. It certainly does matter where they come from and go to, though. Alright, so that's the basic Diels-Alder structure, and that's the way we want to arrange the double bonds from the outset. So that's what I'll do here. I'll rearrange this so that the double bonds are going to show their interactions more. Alright, so we're looking at the same kind of arrangement of arrows. And these arrows here are heading into the spaces between these two carbon atoms. If you like, it can be helpful, I think, to maybe draw in the carbons that make up the end of the diene and the carbons that make up the double bond of the dienophile. That way when they join together you can see where they are a little bit more easily. And you can see if we follow the arrows, this is what we're going to end up with. I'll draw in those carbon atoms again as well. Let me draw that a little bit better. That's better. Now, since this is a cis dienophile, then we're going to end up with the cis ring. And since attack could come from either above or below, then what we're going to see is either these two will be wedges or they can be dashes. Make that a little bit more. There we go, it's better. A bit less confusing now. Alright, so there you go. That's going to be the stereochemistry of the ring. And you can see these two carbons that have joined together, and these two carbons have joined together. And then you can see them in the product as well. And in the case of the trans, again we draw these, they're pretty much already right, but we draw these in such a way that the double bonds are going to interact, and again I will draw the carbons at the end of the diene and the carbons on the double bond of the dienophile. And again we can see the way that the arrows go. And you can see how this will end up. Now it's worth saying that the double bond we get at the end here is of course flat, so we don't put any stereochemistry on these groups that are connected to this double bond because it's completely flat. And because we had a trans, you can see that we're going to end up with a trans ring, which means one will be sticking up and one will be sticking down. Just like before, we could have the reverse, we could have this one sticking up and this one sticking down. Now let's go back to the initial diagram that we had over here. And I just want to point out that because we've got the HOMO here of the diene, and this is the LUMO of the dienophile, you'll notice that the attack comes in from above here, or it could come in from below as well. But because it comes in that way, that's what causes the difference in the stereochemistry. So let's say we've got this being a cis. That would mean that this was sticking out here and we have something sticking out here. You can see that what's going to happen is these orbitals are going to join together, and once they've joined together we end up with a ring, and I'll just sort of draw the bonds in where the new bonds are, and you can see how the stereochemistry will be maintained even after these two bonds have formed to each other, and that's why we end up getting the preservation of stereochemistry. And as if this was trans, again we'd notice the same thing. I'll show you that. Cross that out. And you can see what it's going to look like for trans. If this is trans, then this is going to be sticking out here. Now remember, there's no free rotation about this bond, so if it's stuck in this fashion, put that out there and then stick this out here. And now you can see how the trans orientation of the dienophile is maintained even throughout the formation of the product. And that's why we're getting this preservation of stereochemistry that I've been talking about.